this is a talk which is out of the field, so it's more at a colloquium level, and I prepared it for more like for students in mind, so I hope it's okay for this audience.
You have to press the buttons on the computer. You have to press the arrows.
Not this?
So this doesn't work. That works for the pointer.
I'll start with the motivation and background as to what are anyons and why there is so much of interest in anyons these days. Then what I make it work. With a brief motivation and background, and then I'll describe a particular model called the Kitaev model. It's a one-dimensional model which is an explicit model for Majorana modes, which are the simplest kind of anyons, non-abelian anyons that you can have in this. Then I'll discuss the realization in semiconductor wires and the current experimental scenario. And then I want to briefly mention other non-abelian anyons like pyrofermion, which are things that I work on. And in the last part of the talk, I'll tell you a little more about topological quantum computation, give a general model of anyons, fusion, grading rules, and explain how you can get unitary gates through a combination of grading matrices. So let me start by starting with what are anyons. Most of you work on elementary particles, so they're either fermions or bosons. And you know that the wave function, if they're bosons, will have a plus sign, and if you interchange particles at two different points, they'll have a minus sign of wave functions. But for emergent quasi-particles in condensed matter systems, this is not necessary. And the simplest generalization of bosons and fermions are what are called abelian anyons that can have complex phases at interchange. And this was known as early as 1977. Why is this possible? If you think of adiabatic exchange as an adiabatic process of taking two particles, then what you see is that if you normally, in 3 dimensions, if you exchange particles twice, you come back to the same position. But that's not true in 2 dimensions, because if you just try to interchange 2 particles on a plane, then you actually have to go through the position of the other particle to exchange. The point is that if you have a hole in the plane, then it actually makes sense to count the number of times to go around the singularity in the plane. So there is a difference between 2 dimensions and 3 dimensions, and this is the reason you cannot have the loop. The way we understand it is that if you think of the loop which is formed by taking one particle around the other, you can actually just move it around adiabatically and shrink it to a point, whereas that is not possible in 2 dimensions. This is the reason that you can get anyons in 2 dimensions. This is what leads to anyons in statistics in 2 dimensions. And as I said, the distinction, mathematical distinction, is that the removal of the origin, a single point, in 2 dimensions makes the space multiplicative. And you can count the number of times you go around the origin. So particles in 2 dimensions are classified in terms of the braid loop and not the permutation. You can go any number of times around each other and you will never come back to the original configuration. So the braid loop is the group that you make of paths through configuration space. And the easiest way of understanding what the braid group is via pictures, which is what I do over here. You can just think of what happens if you have 4 particles and you think of the elements of B4. You can kind of have them go, and putting them on a line for convenience, you can have one particle exchange with overcrossing or undercrossing with the other. And these are all elements of the braid. There are actually three generators of the brain group for B4 because you can exchange 1 and 2, you can exchange 2 and 3, or you can exchange 3 and 4. And these form the three generators of the brain group. You can have an identity element. You can have an inverse element because overcrossing is an inverse of the undercrossing. So both of these are also possible. And it forms a group structure because you can have them one after the other. You have these Yang-Baxter relations. You can show that the product of the overcrossing and undercrossing can be actually pulled back to just the identity. So all of these can be shown in terms of pictures that you can, even this kind of relationships can be shown.
So the grade 2 with n strand would have n-1 generators?
N-1
Yes.
and any element can be created from it. So the important point is that for bosons and fermions, once you exchange particles twice, you can forget that you exchange at all because you come back to the original configuration. For anyons, that is not possible. The entire history is important of what has happened from the beginning to the end. So this is the reason even a system of free anyons is actually a many-body it's like an interacting system because every particle has an interaction with the other via this statistical interaction.
So if one takes the phase to be rational number, then does it simplify?
I mean, it has to be a rational number, I guess, but it doesn't simplify, right? But
Because after 3, let's say, it would come back.
after a certain number, sure, but it will still be interacting with as many particles as you have. Right? In general, I would assume that it has to be rational number. So, the point is just like just fermions, having fermions and bosons itself leads to all the kind of new phenomena that you see, like plus and minus sign is important because that's what leads to metals, insulators, superfluidity, Bose condensation, etc. So you can expect that because of this anionic phase, you can get lots of phases in matter. And I also wanted to mention that you also have what you call mutual statistics in two dimensions. Because even if you drag one particle around another, you will still get a phase, right? One can get a phase for taking particle A around a particle B. It's not just, I mean, you don't have statistical mechanics, it's not identical particles, but you can still get a phase if you take particle A around a particle B.
These atoms have to be charged when they reach.
Anyone have charge
They have
under?
to be charged.
They don't have to be.
They don't have to be charged. You can just think of them as being charged.
Yeah, you can think of them as, I don't think they have to have electric charge.
So they don't have to be coupled to any long wave cage.
Hmm?
They do not have to be coupled to a long wave cage.
They don't have to be coupled. The thing is that there's a statistical gauge field which comes about if you think about it, and if you put this theta in it, then one way you can understand this theta is that you can think of it as a statistical gauge field, and then it acts like a Q1, but it doesn't have to be electrons. The point is you can have anyons which acquire just a phase and then exchange, abelian anyons. But if you have things like spinors and so on with other quantum numbers, you can have higher dimensional representations of the brain group. And that means that you have a degenerate set of states with the particles fixed at positions. So it has to have another internal quantum number like spin or etc. And if you exchange these non-abelian anyons, then it leads to a rotation in this ground state. So this was also noted many years ago. And the thing is that these were popular in the 80s and 90s and all, and I worked on them at that time. They became popular now because of the fact that they may be relevant to topological quantum computation. And for that, let me just very briefly mention what's a quantum computer. It uses qubits instead of classical bits. And the qubits represent the state of the wave function. For instance, the spin half, which can be in a state up or down. And unlike classical qubits, the thing is that unlike classical bits, the qubits can also be written as a superposition state of these up and down states. And more commonly, this is usually written as alpha 0 plus beta 1 because the two states of the qubits are usually referred to as 0 and 1. So, yeah. And for the non-abelian anyons, if you have a two-state system, that is what makes your qubit. I'll come back to that. So what you have to do is prepare the system in one ground state, exchange two quasi-particles by this unitary representation because they, I said that they, under a braiding, they go through a unitary transformation and then go to the other state. So these unitary transformations are like the quantum gates. So the states are the non-abelian states are the qubits. The unitary representations that transform them under the braid group are the quantum states, and that are those are the building blocks. So this is the reason for the current interest in this. So now, with that basic background, I'll talk about a simple model for what are called Majorana modes, which is the simplest one.
So the idea of implementing this gate is actually physically move these anyons.
Doing this, which is what I showed. So, yeah, these are the simplest non-abelian anyons. And of course, all of you know that Majorana fermions were introduced originally in high energy physics as possible new elementary particles, right? Which could be their own antiparticle, like neutrinos. If neutrinos did not have a mass, they also had supercelebratory particles of photons. In condensed matter systems, actually what they call Majorana particles are not even fermions. They are modes of the system which are actually non-abelian anyons. They are not fermions. But the name stuck because of the fact that they are very conjugate. So one should remember that when people talk of Majorana fermions, they sometimes even call them fermions, but they are not fermions. So let me start with the Kigayan model, which is the simplest model that you can write down for Majorana modes. And essentially, it's a quadratic Hamiltonian in one dimension, one spatial dimension. And it's like, it has a chemical potential term, it has a hopping term, T, Cx dash Cx plus 1. X is the site index over here. And then there is what is called a superconducting term, which is basically like a hopping term, except that it doesn't, both of them are, it's not, one is not creator and destroyer, it's just like a superconducting term. Okay? So this is a quadratic Hamiltonian which can be written down. I can now write any of these are just the normal fermion hopping operators. I can write these hopping operators in terms of the real part and the imaginary part. So any complex fermion you can always write as a real and an imaginary part. These are still fermionic in the sense that they satisfy anti-computation relations, but they have gamma squared as 1 and gamma dagger is gamma. So they are not real fermions. The complex fermion is a fermion, but these are not just the real and imaginary part, which are what is going to be a Majorana.
A and B represent what?
A and B are just two. This is a real part and the imaginary. I'm calling them A and B. Right? Any fermion at the site X can be written in terms of its real part and its imaginary.
And delta is a parameter. Delta is a parameter.
Delta and T are parameters. T is a hopping parameter. Delta is called the superconducting parameter. Mu is the chemical potential. So now I'm going to rewrite this model. I can rewrite. So the idea is to think of fermions on a site being made of two Majorana modes. And what we're going to do is change parameters in the theory so that the fermions get fractionalized and they get separated. I'll show you how that is done. First, let's think of the parameter mu less than 0. This parameter mu less than 0. And T is equal to delta is equal to 0. And I'm going to rewrite this Hamiltonian. So it just has this term. In that case, what you see is that the model can be, the Hamiltonian can be rewritten as just in terms of the A and B, real and imaginary parts at the same site. So that's what I'm showing by this kind of a coupling. On the other hand, I can also choose other parameters. I can take mu 0 and T is delta. And then what I can do is that if you rewrite the same Hamiltonian, what you see is that it actually has couplings. This T couples the B Marana at one side to the A Marana at the next side. And this entire Hamiltonian is independent of these two modes. And I can now think of this as a new kind of a fermion. Right? I can create, these kind of things are sort of a new fermions defined on nearest neighbor sites. So the state is highly correlated in terms of the original fermion, but in terms of the new fermion, it's very simple. And I can even make a non-local fermion from these two modes which are left over. Right? Because I can take the A mode on the first side and the B mode on the nth side and make another complex fermion. And since this Hamiltonian does not depend on this non-local fermion, the energy of this Hamiltonian is independent of whether this state is occupied or not. So what you have is a non-unique ground state. That is, the ground state is doubly degenerate. Either I can call the vacuum state or B dagger of the vacuum, both of them will be degenerate. Right? So I have a non-degenerate state. So for some parameters, it is just like it will have a unique ground state, no edge modes. For some other parameters of the theory, it has the doubly degenerate ground state and edge modes. And in fact, this is the main point. Because it has no dependence on the n Maranas and is independent of whether the non-local fermion at the edges is occupied or not. It's a doubly degenerate fermion, and these are both fractions of the original fermions. So this was Kitaev's magic trick. He found a model where by changing parameters in the theory, you can fractionalize the fermion and put different parts of them at different sites.
So I didn't understand. What does it mean that you fractionalize the method? This non-local fermion was just a linear combination of the fermion field on the first and the nth side, right?
Yeah.
But why do you say it's fractionalized?
It's okay. It's at different parts, or it's a non-local fermion.
I see. So why is it so surprising that the Hamiltonian has 1 degree of freedom on which it doesn't depend, and there's some degree of freedom on which the Hamiltonian doesn't depend?
Why is it so surprising?
Yeah, why is it so hard to construct a Hamiltonian which is just independent of
No,
1
it's
degree?
not hard to construct. I mean, the thing is that because it's constructed, this is the simplest such thing which can be constructed. Where you can see very easily. It can be done. Right? That's what happens. So the point is that because what I'm trying to say is that these two can now move independently. They are at different parts. Right?
Okay.
Can they move? I thought you were stuck to the edges.
They're stuck to the edges, but they're independent. I mean, okay. Once you've created, you can think of them as moving independently. The edges of the system can move, right? They're connected by one wire. They're connected by a wire, but okay.
You maybe like moving inverters or something instead of moving. Like I'm just confused. So if you have a wire,
Yeah.
like I thought in the entire topological case, not just in this Hamiltonian, the wires were stuck to the two edges, right?
Yeah.
So how do you?
Now you want to, I'll show.
Okay, you'll actually move the physical wire?
But no, you'll actually change parameters.
Oh, okay.
You'll make them topological, non-topological, and
So the original Hamiltonian was quadratic in the fermion, the original
what?
form.
It's constructed
And
originally.
it's quadratic, and it's still
As
quadratic.
so it can be solved
Yeah.
fully for any, in fact it can be solved for any, there's a range of parameters for which it can be solved. For this, for mu greater than 2t, you find that its system is topologically trivial. For mu less than 2t, it is topological and has doubly degenerate ground state. Plus, yeah, this is the doubly degenerate ground state. Zero. This is the Marana.
You always see delta equals t. You always see delta equals t
Delta?
equal to t.
No, that's what I'm saying. You don't need delta equal to t.
Okay.
I put it as for simplification.
Okay, yeah.
So you can do it for, it's a quadratic code, you can solve it for any.
So
There's a range.
so even the excited states can be,
Huh?
even the excited states can be,
Yeah, fully satisfied.
it's just fully integrated.
Yeah. And I put delta equal to t, but that's not okay. Otherwise it's square root of t squared. So now the question was that this was a toy model. We wanted to construct a realistic model with these kinds of, the same kind of behavior and look for the wire. That was the.
So what is this graph telling us?
Huh?
What is the graph?
This graph is as a function of mu, that there is a entire, I did it for two specific cases. It's telling you that there's an entire parameter region which is topological and an entire
Okay, but what are
parameter.
these lines?
These lines are just the energy variable states. I mean, I've plotted energy.
The topological phase, it looks like there is no signal.
Huh?
Oh, I see. These two combine.
These two combine.
Okay.
This is what is called the BDG spectrum,
I see.
right? Totally voltage spectrum. So this is energy versus. And I want to now say why these edge N0, Varana 0 modes are relevant for quantum computation. I mean, they are firstly degenerate, the occupied and non-occupied are degenerate, and that forms a qubit. Whether it can be occupied, not occupied, forms a qubit. It can't be disturbed by local disorder because of the fact that because there are two edges of the wire, to change its occupation, some kind of disorder at one end will not change the other. You need the entire state to be changed to go for quantum.
Can this be said in terms of entanglement?
Hmm?
Can this be said in terms of entanglement?
I mean, it's a single period. Right? This is a single period.
So now,
Right, so,
Sorry, one question on the previous slide,
yeah.
the slide before that. Yeah, what do you mean by spinless fermion? Yeah.
Okay, what I meant by spinless fermions is that the model has only, I mean, we are not talking here about whether it's only one kind of fermion, right?
Yeah.
So I'll just explain how will you do it. So actually what you need is a P-wave superconductor. So you don't need the degeneracy is coming because of something else, not because of up-down spins. So normally the thing is if up-down spins are degenerate, then you won't get this physics, right? So you need to split the up-down spins, make it spinless, and then put in this.
so just to go back to Suraj's comment where he said, I mean, why is it difficult about one can just make have degree of freedom at the end?
Yeah.
But I think isn't this, I mean, the non-trivial part is that a single degree of freedom lives at two ends, right?
Single degree of freedom.
Which is something
But
very
you can always define a degree of freedom to be A phi f1 plus phi f n.
But it's part
Not
of
defined,
a, both
single
together
qubit
form a
which is-
single fermion.
Everyone?
They form one fermion, right? State.
Correct. But
No,
can't
no.
we define a non-local degree of freedom even if you have local degrees of freedom and then define some canonical computation relations for it? Like if I take A1 plus AN,
You can do that. I mean, but how many physically you have to get this? Right? That's the
yeah, maybe the point is here, you have local Hamiltonian, but somehow it becomes
you need
independent.
to have it. So yeah. So before I come to the physics system, now let's assume that we have these isolated Majorana modes at the edges. That's what I call Majораnas. One can make composite anyons by fusing two anyons into either the vacuum or one fermion. So this is why it's called a non-abelian anyon. The fusion of two, the bringing together of two these things. If you bring them close together, you can either make a vacuum or a single fermion. So it's called non-abelian. And
So
the
any
grading
equal-
comes here.
Yeah.
Supposing I have two Majoranas belonging to the same fermion, I can braid them. I can also braid two Majoranas belonging to two points, two different fermions. I am now thinking of the edge modes as independent particles, which are moving on the edge. Right? They are connected in some sense to the other, which I have put over here. Because there is a quantum number which will be conserved, which I will come to. Right?
Should you could just like different wires being slightly coupled or something, and then you're moving the wires around the.
We'll have to see how to do these.
Okay.
These are all still proposals, right?
Okay.
Physically. But yes, we have to move them around in some way. But right now, what I've said is let's assume that there are decoupled Majoranas which are free to move around. Then you can braid them.
So I didn't understand. This one is gamma 1 and that is gamma n.
No,
picture?
gamma 1, gamma 2, gamma 3, gamma 4. I have 4 Maranas.
Oh, so all of them is one, so each of them represents a delocalized particle.
Each of them represents an edge mode, end mode,
Represents an edge.
end mode, and they're independent to move. That's it.
And the
So
part
I'm
that is,
exchanging
the part that is circled is one
one
dimension.
formula. I can, yeah, do it as well. I'll come. So you can either break bananas belonging to the same formula, or you can break them belonging to different formulas. I'll come back to this. And so now what I want to do is find the operators that do this break. So what happens when I exchange two fermions, right? If I, under exchange of two fermions, what kind of an operator will take it from one to the other? What is the breaking operator? So the gamma 1 goes to, can go to e raised to I phi gamma 2. And with the exchange operator, which I am calling U12. And originally this phase can be chosen to be 1. I can choose this phase, first phase, I can choose to be 1. But then the phase of the other exchange, gamma 2 going to gamma 1, is determined. It is forced to be minus 1 because the product of gamma 1, gamma 2 is forced to remain unchanged. Because I've said both of them belong to the same formula. If gamma 1 and gamma 2 belong to the same formula, then it's exactly what I wrote, right? One fermion is written as gamma 1 and gamma 2 are what I earlier called gamma A and gamma B, right? So I can rewrite this in terms of the non-local. You can think of them as the edge formulas also, right? So the two of them will form a single fermion, and because they form a single fermion, gamma 1 has to be written as d dagger, gamma 2 has to be written like this. And if I take this product of I gamma 1 gamma 2, it is fixed by the fermion number. Fermion, not exactly number, because we have superconductivity in this. We have a delta term. We can only talk about fermion number modulo 2. So this is called fermion parity. So this is fixed by fermion parity. If this is if the state is not occupied, this is 0 and this is fixed to be minus 1. If this state is occupied, it is fixed to be plus 1. So I can, when I exchange two Bajranas, if U1, this goes to gamma 1 goes to gamma 2, then gamma 2 has to go to minus gamma to keep this fixed. Right? And now I can, yeah, so that's what I said. If gamma 1 goes to gamma 2, then gamma 2 has to go to minus gamma 1 to keep this fixed. So this is our exchange operator. And this can be implemented by this U12 in terms of this gamma 1 and gamma 2. If you add this U12 on this, you can see that this exactly implements what I'm saying. Right? So I can write this also in terms of the fermion operators, and this is exactly U12 in terms of 1 minus 2n, where n is d dagger. Right? So now on the other hand, this cannot change. The fermion parity cannot change. So on the other hand, if I want to really show how things move in the degenerate subspace, I have to have a minimum of four Majorana modes, gamma 1, gamma 2, gamma 3 and gamma 4, and then consider various exchange. From 4 Majorana modes, I can make 2 normal fermions, right? Because it has enough degrees of freedom. It has 4 real degrees of freedom, so I can make 2 normal. And so the states of the system are now given by d1 dagger n1, d1 dagger n2 acting on 0, 0. So these are the kind of states I can have when I have 4 fermions, 4 Majorana's in the picture. So these are all the 2 fermion operators, 2 fermion states. Now I can, if I do the exchanges, I can see that if I do U1, then this just gives me a phase. But on the other hand, if I interchange a Majorana from one fermion to another one, then it is possible for me to keep the fermion parity fixed and still move in this degenerate space. Because there are now, it's the n1 plus n2, that both of them can be 0 or both of them can be 1, right? Both can be 0 or both can be 1. that is allowed. And you can move in this space. And this is what gives you non-abelian grading. Right? So this will just give you a face which is not useful for grading. So you need a minimum of 2 qubits to have grading, non-trivial grading in this system.
Here one can also consider 1-3,
Hmm?
1-3 grading also.
1-3 grading. You can have 1-3 grading. You can have, 1-3 grading will be the same. You can work it out. It will be similar to 2. Yeah, it's the same fermion account. So if you have multiple Majorana's in the system, as long as you can grade Majorana's from different systems, you will move in the degenerate reception.
So in terms of this grading picture that you had, this would be then this would be a grading with 4 strands and
4 strands.
and this and each strand would have how much 4-dimensional input space associated with it.
No. This is grading in a 2. You're only grading between as far as it will be 4 strands because you have 4 of these systems. And it's the only non-trivial grading that you're getting is between one of these. Right? Either 1, 3, 2, 3, right? Those categories. You can probably rewrite it in terms of the generator and not right. So the point is this is the point. Grading of Majorana's perform unitary operations which are useful for quantum computation. So the idea is that you can create, to start with you can create 2 Majorana pairs, then break them and you go to a different state in the system. Okay? So that's that. So that is what is topological quantum computation. You use non-abelian anyons, qubits formed from the occupation, non-occupation of the non-local formula, and the quantum gates are the unitary grading matrices which can change the qubit. And because the different pieces of the formula, it's a non-local formula, the occupation of this state cannot be easily changed by local formula. So the qubit is topologically stable. Stability is of course proportional to the length of the wire. And grading also cannot be changed by, because it only depends on whether things are graded or not on whether, it doesn't depend on where it's graded. So this is what they call topological protection from decoherence, false errors. So fault tolerant topological. So it's supposed to be easier for scalability. So now let's see where to find or how to engineer, where experimentally one is in this field. So what people try to do is basically mimic the Kitayan model in different kinds of physical systems. The simplest physical system where you can do it is in semiconductor wires and with a strong spin-orbit coupling. Firstly, because to mimic the Kitayan model, what you see is that you need a magnetic field to split the plus and the minus, so that in some sense, I want this kind of a picture, where I have only a single node, not 2. Right? And in real life, you only have S-wave superconductors, you don't have P-wave superconductors. So you need to mimic a Kitayan model using only the S-wave superconductors. So what they found is that if you have S-wave superconductivity, then it couples up and down spin. Now, if you put spin orbit coupling, then what happens is you can split these up and two opposite spins away from each other, and then you can have your spectrum can look something like this, and this will have some component with an up and down, so that it can couple to a spin. It's not exactly here. It was exactly you need an up and a down this way. Here, even though you have a single you can probably, because these two have some component in up and down, you can couple to a switch superconductor. So this is the way it's actually engineered to mimic the Kitayan model. So you expect to have Majorana's at the 2 ends of it. And the theoretical proposal was that if you have tunneling from a normal lead into this edge, you will actually get the biggest is some signature of the Majorana mode at that point. And so you expected a zero bias conductance of 2 E squared by H. So this was proposed in 2010. And around 2012, there were many experiments which said that they had seen it. A lot of experimental papers came out which said that they had seen signatures of Majorana fermions and so on. But many of them were retracted and most of them could not be reproduced. Oh, sorry, I'll finish. And then,
10 minutes.
yeah. So now one knows that you can ask the question of Majorana's, have they been finally seen? There's a paper by Microsoft Group in 1984 which says that by a combination of local and non-local transport measurements, there's a high probability of having seen it. So now they're more careful and now they're not saying that proven it consistently, but they see it in roughly half of the 25 samples studied.
So what makes it so difficult to see? Is it has to be low temperatures or?
There are many other things which can also mimic the Majorana mode. It's basically just a zero mode, zero energy conductance peak, and there are other ways that people can get it. That's what happened initially. Now they're saying that they can see both the peaks at both ends, which was not seen initially. They also see the gap closing and opening. They've seen all that, but other groups are not reproduced. And Microsoft has not released all its details. So until other groups reproduce it,
But the technology is only like a few labs in the world that can do this.
a few labs.
And people want to follow Kitao model, basically want to reconstruct Kitao's model in the lab, or are there other ways also?
There are other ways that people are trying, none of them have succeeded. Basically, simplest is the Kitao model. That's hasn't succeeded. So, okay, as I said, I believe it has been seen by the jury is still out. And if you want to see how to break this, then this is done by changing parameters in the theory and putting another one, moving them aside and so on. So there are, people have come up with these techniques, but as of now, the Majораnas are not, you are not nowhere near doing any of these things. And okay, what about more exotic non-abelian ions such as this? And panafermions, for instance, braiding of the qubits, a singular gives you only some kinds of brains. It doesn't give you universal quantum computation. For that you need more exotic anyons. And panafermions allow for more gates. Fibonacci anyons, one can get universal topological quantum computer. And there are also, proposals in using quantum Hall systems to engineer Majorana.
What if Fibonacci?
Huh?
What if Fibonacci is?
Fibonacci also, there is a Fibonacci anyons exist in 12.5 fractional quantum model. People think. But again, that's a very hard state to even obtain, leave alone have excitations. So these things are still proposal states.
Why is it called Fibonacci?
Alpha. Yeah. So the Majorana modes which are can be engineered in mu is equal to 1 quantum Hall state. I won't go through this. You can get superconductor and spectra and try to manipulate. You can also have panafermions if you put fractional quantum Hall effect. And I'm only mentioning this because this is where I recently worked on trying to look at panafermions and fractional quantum Hall. What happens to them when there's X reconstruction and so on. And with that, let me come to the last part of the talk, which was the general model of anyons and how they get used for topological computation. And the general model is that what happens is that you start with the general model of anyons with anyons labeled A, B, C, etc. And you can have rules for fusion and these fusion rules are just, these are non-negative integers. But usually NCAD is just 0 or 1. And for abelian anyons, there will be only one way to fuse, but if it's for non-abelian anyons, there will be many ways to fuse. Fusion is commutative, and you can fuse multiple anyons and see what happens. and you get things like the quantum dimension, which I won't go to over here. I just want to mention that these don't have to be real numbers, because even for Majorana's it's square root 2. Because single fermion has dimension 2, right? It can be 0 or 1. So for Majorana's it will be square root of 2.
It feels like the arrows are the opposite of what I would expect.
Yeah, I've drawn it as splitting.
Yeah, is there a reason for this?
This is called splitting.
Yeah, but why it was pretty confusing?
I just picked it up from
Okay.
I didn't draw it.
Okay, fine.
Actually, I should have done, but I just picked
Okay.
up from paper. Yeah. Fusion rules are associative. So there are these F matrices. When we have this is the part I wanted to mention, because it's probably closely related to a lot of things you do in string theory and conformal field theory. So you have these fusion rules which can be associative, because you can fuse them in one way or you can fuse them in another way, and they are related by these F matrices, which is just a basis change matrix. And to make the F matrices consistent, you need to look at 4 anyons, and then you get something called a pentagon equation of how these, because you can fuse these first and then go change to this or change to this, and the same thing you can also go through a different direction. And this way you get something called a pentagon relation. And if you have more anyons, you don't have any more consistency. F matrices are enough. And then you also have rules for braiding, and what happens when 2 neighboring anyons are exchanged. Then you have these things called R matrices. Then you swap 2 anyons at a time. And these are, since exchange statistics depend on other anyons in the system, it's not, because these are not linear. So they're not just a phase. And again, for this you need consistency conditions, and there are these things called the hexagon rules, which is again the way you go from one to the other. In different ways you can do, which gives you the hexagon rules. And the solution of the pentagon and the hexagon rules, this is a complicated set of equations in terms of the F and R matrices. And this is what is supposed to define your topological quantum field theory, and there's no general solution, because these are not fully classified yet. But for any given model, it is possible to solve the consistency conditions for the F and R matrices and compute what are called the topological invariant, the S and T matrices, which define the topological phase.
So in math literature, this is called blended tensor technique, right?
Universal tensor category, something. Unitary tensor. Modular, okay.
Modular tensor category.
Modular unitary tensor category.
And I think there are some papers in math which tries to classify dimension by dimension, dimension 4.
Yeah, in fact, somebody else was telling me that, yeah. I'm not sure. Because at the level at which we work, it's just with matrices on paper. I don't want us to be the full mathematics.
No, I mean just the solution to the
Yeah, just the solution to the F and R.
pentagon example.
Yeah, very nice. And yeah, so we had defined this exchange phase as so I can create an anion anti-anion pair, 2 pairs of them, exchange the 2 anions, and then I can get the phase. I can also compute the S matrix, in the sense S is something where I can create an A anion and a B anion, exchange them, take one around the other, and that also gives me this SA. And these are S and T are also probably related to what, because the anions also can be related to punctures and torus and things like that. So that's where the names S and T come from. So to recap, what you can start with is an anion model. You define fusion rules, associativity and F matrices, define braiding and R matrices. For consistency, you need pentagon and hexagon rules, and this is what defines the model for you. And by solving this consistency condition, you get the topological split and the Michel space. Okay. And now the last part is just to say how it can be used for quantum computation. And these are things that we haven't explored, and relations to many other mathematical things. And I'll just give the models that can get solved very easily are something called the toric code model, has excitation with mutual abelian anyon statistics. The Majorana model that I talked about, Fibonacci model with just 0 and tau, Z3 paraformial models, and generally Z8. And to do quantum computing with this, the simplest way is to think of a model. This is the Fibonacci model has just this very simple fusion rules. It's tau cross tau is 1 plus tau. This is the non-abelian part. So this is the vacuum. 1 is the vacuum. Tau is the non-abelian. It has only 2 states: a vacuum and a non-abelian part. And there are 3 states possible when 3 anyons are fused, and that will be what will form a qubit. Because if you just fuse 2 anyons, what happens is that this total quantum number is not present. It's the same thing that happened for the Majorana case. Then you can't do anything. We need the total quantum number to be the same. Only when the total quantum number is the same, then it can be used as a 0 and 1. But since there are 3 of them, there is one more state which is called a non-computational state, which comes into the picture. So these 3 form your qubit. And then the idea is that you can now write down any kind of, you can solve the pentagon equation and the hexagon equation, and you can find out that the only non-trivial F matrix turns out to be of this form in this tau space. And then, so you can, okay, let me come to this. In the basis n, 0 and 1, you can find out that there are 2 kinds of braid bases, right? And using this, you can, any arbitrary braiding quantity is just a combination of these 2 matrices. Since any arbitrary braiding operator can be created, any unitary matrix can be reached. So what you can do is you can start from any state and go to any state via these braiding operators. Those are the unitary topological gates that we have. So yeah, I'll end with just this story that in March 2020, Preskel made a bet to be settled on March 1st, 2030 at midnight, where someone had made a topological quantum theory. The stake is only a pizza and a beer, but at least he made the bet. Yeah.
So I have heard this claim many times that some of these topological states are protected, so
Yeah.
once you create them, you can do whatever you like. But if they're so protected, why are they so hard to create? We're missing something.
Fibonacci, of course, I mean, you don't even know how to create it. I mean, you have to engineer it. The problem is in engineering is the maths is easy.
No, but how do you try to engineer them? I mean, that how decoherence, decoupling, noise, with all these things, can you actually engineer them, or there is something we're putting under the rug that we're not critically thinking why engineering a big topological state
Because these states don't exist. Even for Majorana, which exists. For instance, if nu is equal to 5 half, if you think of its excitations, they are Majorana. You can have these Majorana states. But actually creating a nu is equal to 5 half state itself is not easy, right? I mean, you need very low temperatures, very clean samples.
Why do we need clean samples?
Because otherwise the state itself will be unstable. I mean, the quantum Hall state. For instance, I don't think in India we still have places. Now, maybe the only way I can think of, I mean, if you do want to do it to semiconductors, the temperatures that are required, the samples that are required are too far off right now. One possibility may be if they can get in graphene samples, but there are no serious proposals yet in graphene of how we will do it. Maybe there it is possible. I don't think the problem is with the math, it's more with the actual.
I think Kallar is saying probably, if I'm not mistaken, that the difficulty that one is facing in constructing these things, won't that come back once you claim, let's say I have constructed it, wouldn't that come back and make the whole system not so stable that you had hoped for? Because the fact that there's difficulty in constructing things, sample being this and that. So that just means that even once you constructed it, it is going to be as unstable as
like even for a semiconductor bio.
Yeah.
Yeah, I mean the fact that they find it so difficult to really make this Majorana modes, even see Majorana modes.
Yeah.
Because there are very you say it's stable, but there, if there's any contamination of outside fermions, that can maybe change the system and so on. Right?
Yeah.
Those kind of things. Yeah.
So in what sense, okay, in mathematical sense, it is some, one says that the disorder doesn't affect it, but all this difficulty is that is there in constructing those would also need to.
The hope is somehow you will manage to realize the entire model in some clean system, and then you
Yeah.
will get the stability.
Yeah.
But it's not
Obviously,
really-
it's not magic that you will do something and suddenly get something topologically stable.
Yeah.
But no,
It
you-
will not be very easy to get. I think you have to, graphene is a clean system. It's easier to get clean graphene than clean semiconductors. Right? So maybe if they can get graphene edge states, right? Those will, and they are more stable at high temperature. Quantum Hall states are another thing that we are looking at, but quantum Hall systems,
They are experimental.
very low temperature.
But they are experimental, people have found one.
No, they're for quantum Hall, of course, but they're not from Maharanas in this.
Oh, wow.
And if you have edge states, you need the edge states, then when you form edge states, what you find is that there is contamination by what is called reconstruction of edge states. You think there is a single edge state, but there are actually other modes, neutral modes, which confuse the issue. So all those things have to be made very clean before you can try to move forward. So yeah, experimentally there's a long way to go. So I don't believe in 2030 will happen.
So also philosophically, I think things which are more stable are harder to make, right? Because if the thing is stable, that means its decay width is very small. So this production cross section is also very small, right? So that may be what is behind this.
So is it true that real electrons are actually continuous speed? So you can't really in principle make a topological state. So you are doing some approximation somewhere saying that things cannot arbitrarily change. I'm not super sure. I feel like they are like free rotors. How can you make something topologically stable by a series of free rotors? If you assume they'll apply Eisenberg speeds, yes, you can make possibly. But really, the question could be how a free rotor, you get something which is not a free rotor.
I thought the idea was to introduce a magnetic field to first split that steel decay.
Yes, so you are doing something and there is certain approximation there, how much you can freeze, how much error is there, so it is, there is a game there.
Yeah, but normally magnetic field
Obvious.
splitting I think is reasonably
Quantum Hall you need.
Yeah, in quantum hall also you are splitting.
You can freeze out the states.
Yeah, okay, splitting eigenstate, I have to think a little critically. Splitting eigenstate may be common, but creating arbitrary combination of them is not easy. Means that if you have 5 speeds, and
So just
it is not easy to make a highly coherent state.
So just before the discussion starts, maybe we can have the top finish.
Sorry.
Yeah, and that's the end of the thing. So at least I hope that it will see this. And this
Has the Moore Reed state been experimentally constructed? Has the Moore Reed Faufian state been experimentally measured? Is nu equals 1 5 half state?
that is usable to find out.
That's been measured
Yes.
experimentally? Isn't that?
So Moodley's,
homogeneous
yeah,
system?
Moodley Faufian will have a Majorana excitation.
Yeah.
The Moodley state, meaning the mu is equal to 5 half state, has been measured, and if people, but they do, I mean the what do I say? The quantum Hall state has been formed, mu is equal to 5 half state, but I think there is still, it's not clear whether it's the Moodley Faufian, whether it's the anti-Faufian. There are 3 candidate states, each of which have different excitations. And I think it is not yet convincingly shown which of those 3 states it is. But the newest 5 half state has been definitely.
Okay.
Right? But there is a controversy there about whether it's Faufian or anti-Faufian or there's a third one. Faufian plus anti-Faufian.
You were saying something.
So I don't know this thing. So basically, maybe my point
has a gap to it.
So,
And the stability will depend on that gap. Right? And that gap in this case will depend on the length.
right, is it common in, do we have any clear example of a quantum system where, and also because hitting one state is easy, but if there is need, but to create a huge gap, you have to somehow synchronize a lot of states. Just creating a huge gap is very easy.
No, I mean, the ground states you can have, right? With have ground states with a gap to excitation, that is possible.
Like superconductor.
So kind of many other, in the only topological ground states as well. Right?
No, but not experimental. I'm being experimental, not theoretical.
Oh, even any quantum Hall states are all topological states. There's a topological insulator, there are these wire simulators, all of these have been found experimentally.
And if there is a little bit of impurity, what happens there? Without creating an effect,
There is a gap, right? So it behaves like an insulator. So if you try to pass current through it, what you find is that the current is only carried by the surface states. You can form a 3D topological insulator where you can't pass current through the system because of the fact that there is an energy gap to creating excitation in the system, which will carry the current. On the surface, on the other hand, there are kind of surface states which don't have a gap, and those states can carry current.
People have made surface codes in the lab. You can have an example of
What?
people have made surface codes in the lab.
Yeah, that's an example. The chlorine code is one example of a surface.
But if
So
some other
probably
surface,
the people, what they will now do, I suspect, is not try to do in real material, but do with cold atom and those kind of things. You can create, again, you want to mimic a guitar, or you want to mimic a surface code. The chlorine code is again a 2D surface code, which has anyons which have initial statistics.
right.
Those codes, I think, can be done by doing this kind of,
It didn't rescue already will.
what?
It didn't rescue already will. Because surface codes have been used for some small computations.
I think they're now trying to use more, I mean, as far as I know that.
Yeah, they have.
Okay, if there are no further questions, let's thank Sumathi again.